Good morning, everyone. So welcome to today's class. Today we will continue to introduce the multi-layer perception. So recall that in last class we finished some analysis on the MLP. We examined some of the commonly seen problems, like including the vanishing gradient, exploding gradient, and also the overfitting. This kind of problem that when you are training MLP actually that frequently occurs. And then how to avoid these problems, of course that should depend on your structure. That is how you design your MLP model. And we introduce like some of the general rules, only general. That means not universal, not absolutely correct for all the tasks, for all the data. Just from our experiences, if we follow these rules, then possibly the MLP will perform well. Like the input layer and output layer, quite straightforward. Then how to decide the number of layers and number of neurons in hidden layer. We can try to follow this kind of rules. Like first, it depends on whether the data is linearly separable or not. If it is linearly separable, there are actually no hidden layer because the artificial neuron is already capable. If the data is not linearly separable, then of course we have to use multi-layer perception, and then it depends on our data. So if it's some simple data, usually we use 1 to 2 hidden layers. If the data has more dimensions or quite complex, then usually 3 to 5 hidden layers. The number of neurons, we have these rules. So the number of hidden neurons is better to between the size of input layer and output layer keeps decreasing, and the most appropriate number of hidden neuron possibly is like the square root of input layer nodes times output layer nodes. These are just some rules from the experience. Some general use case, not universal. Like sometimes when you design your MLP for some specific task, specific data, it's possible that it might just violate some of these rules to find the optimal structure. So actually everything depends on the data, the task, and possibly your own experience on training the model. And here is an example, quite simple example. So suppose we have data like this, training data. So know that this is a two-dimensional data, right? So each sample has like two-dimensional inputs, this x1 and x2, this two-dimensional Euclidean space. And the output or the class label is the color. So as you can see, we have these blue dots representing one color, one class. And then the red cross represents another class. We have two class label. So if we observe such training data, of course, it's not linearly separable, right? You cannot just draw a straight line to separate the two classes. You can never draw a straight line in such 2D Euclidean space. That's not linearly separable. The decision boundary cannot be a straight line. Then what should the decision boundary look like? Actually, there are, again, infinite number of decision boundaries. Like this is one possibility. One possible decision boundary can separate the data correctly is like this parabolic. Another possible decision boundary separate the data correctly is like this. So actually, you can draw as many as you want to separate these two classes because currently we only have 8 data points. Okay, after we know what is the decision boundary, like possibly look like this, the next thing is that we can try to design some multi-layer perception so that it can capture the decision boundary. Like the artificial neuron, actually what you learned at the end for a multi-layer perception neural network is a decision boundary. Decision boundary to separate the training data. Suppose now we want to use an MLP to represent such decision boundary, this possibility, then we know that actually a multi-layer perception is that you try to connect all the neurons together. And each neuron, each artificial neuron can be regarded as a straight line because each artificial neuron itself is linear, right? So that means we try to use some straight lines to estimate such non-linear decision boundary, and then we can get some estimates like this. So if we use such two lines, actually these two lines can roughly represent the decision boundary. And only two straight lines are enough. Two straight lines means that actually the first hidden layer will have two hidden neurons, because each neuron is just one straight line, right? Each neuron itself has a weighted sum, the linear transformation. So we use two hidden neurons to try to estimate this decision boundary. Then we have two straight lines like this. After that, we need to try to find a way to combine these two straight lines together, and we can roughly have such things. So the two lines, we just roughly think that they can be connected by another neuron, because actually that we just try to combine them using, again, actually this is some like linear combination of these two straight lines to try to estimate such a decision boundary. So we can just roughly imagine that now these two lines are connected by another neuron. That neuron would be the node in the output layer. Then at the end, we can design the multi-layer perceptron structure like this. So our input, we already know, two-dimensional input, x1 and x2. And now we think that, okay, the hidden layer only has two neurons would be enough. So that now this neuron can represent this straight line. This neuron represents this straight line. And then we can directly connect with the output layer, because we find that, okay, these two straight lines.
I think I left my jacket here.
Your jacket. Maybe you can find your seat. Okay, it's okay. It's okay. Yeah, it's very cold. Remember to take your jacket. You're welcome. Okay. All right. So we find that two straight lines are already enough. Right? Enough to like estimate that decision boundary. So we can directly connect with the output layer. Output layer, we only need one node to try to connect these two lines together. So at the end, we can design our multi-layer perceptron structure like this. And after that, actually, you can, if you observe these two straight lines, you can directly assign the values to all these parameters from W1 to W6 and theta 1, theta 2, theta 3. Because this data is quite simple. This data is like we only have 8 data samples, 2 classes. It's quite simple to directly assign all the parameters. This is actually what you're asked to do during the midterm exam, right? Directly, like you are asked to give the parameter values because the data is quite simple. Of course, if you want, you can also try to use the gradient descent way to learn of these parameters. Then you need to like do some initializations, set some learning rate, and then according to the updating rule to update all the parameters step by step, epoch by epoch. At the end, you can also learn the parameter values. All right, so any question regarding this example? Great. If no question, then let's move on. Let's try to examine the roles of different components in a multi-layer perceptron structure. So first, the weight. Weight is actually the parameters consist of large components of the weight parameters. So weights are the real values associated with each feature, which tells the importance of that feature in predicting the final value. Right? Weight is always trying to connecting some nodes in the previous layer with some nodes in the current layer. So basically, weight is the edge, and the edge tells the importance of some features. So here is some like empirical results to show the effects for the change of weights. Suppose we only have this perceptron. It's some single perceptron. We only have 1D input, so we have this one edge. Suppose it's W, the weight parameter, and this perceptron itself has the bias parameter theta. So let's get the output functions by setting W to different values. So we select, okay, W to like 0.5, 1, 2, 3, and we always fix theta to 0. And suppose we use the sigmoid activation function. So if we use the sigmoid, actually it cannot call perceptron, it's called neuron. But anyway, I think you can get the meaning. So now we use this one, and then we try to plot the different output functions using different weights. So basically we have these 4 functions. Let W to be different values, and after that we can show the results like this. So since all of them use the sigmoid activation function, so of course all of them have this S shape, and actually they all intersect at this point. So when X is 0, a sigmoid X is always like 0.5. This doesn't change, but we do notice some differences if W takes different values. We find that the steepness of the sigmoid actually changed if we set W to different values, right? So this black curve, that's F 3x plus 0. So when the W takes the value 3, actually it's the steepest. And if we decrease the value of W, right? Like if we have the red line here, that's F 0.5x, actually is the least steep. So that means if we already fix activation function and fix the theta, the bias, then the W controls how steep the activation function is, or how steep the output is. So this is the effects, or this is the role of the weight parameters. So according to this example, we can just see that, okay, now the weights control the steepness of the activation function. So actually that means if you learned some very large weight parameter W, then that means actually your output is very steep. If you learned weight parameter W is very small, and that means your output actually is quite like smooth. This is the different effects of different weights. And let's see the role of biases. In this case, we always set W to 1, and we let theta to be different values. Like here, theta can be 0, 1, 2, 3. And again, we just use sigmoid activation function. We always fix other components. And then we can plot the output function. So all of them, again, S-shape because they are sigmoid activation function. They do not overlap, they do not intersect at 0, 0.5 anymore. But we find that now, since W is always 1, so actually the steepness is the same for these 4 functions. The only difference is that they shift in the x-axis, right? Like this is f1x plus 3, so it's shifted if we consider with this red one. This red one with theta is 0, so it keeps shifting in the x-axis. So through this example, we can see that actually bias is just for shifting the activation function towards left or right, depending on the value of theta. And previously, when we are learning the artificial neuron, we also mentioned that this theta, this bias term, is like does not rely on the input actually, because it's some parameter associated with the neuron itself. So that means after the weight parameters and the activation function already decide the output steepness, the output shape, then the theta, the bias, can try to control the output by shifting it in the x-axis. So this is the role of the bias term. So until now, any question regarding the effects of weight parameters and bias parameters? Great, then we still have one thing remaining, that is activation function. We know that for a neuron, of course it has many parameters, the weight and the bias. There is another very essential part, is the activation function. Each neuron has its own activation function, and activation function is very important in the neural network model. So the choice of activation function in the hidden layer has large impact on the capability and performance of the neural network. Because the activation function, it defines how the weighted sum of the inputs is transformed into an output from a node. And in this case, we have to carefully decide our activation function, right? Actually, in the midterm, the last question, you also see that if the activation function you didn't choose it's very good, then basically the multi-layer perception, it just collapses into some single neural model. Then this is some rules that we can follow to design our activation function. So first, all hidden layers typically use the same activation function. That means you just choose one activation function for all of your hidden layers. But of course, the hidden layers will be different from output layer. So the output layer will typically use a different activation function from the hidden layer because the output layer's activation function is dependent upon the type of prediction required by the model. Later on, we will also introduce, like if we have different prediction tasks, we should use different activation function in the output layer. And then typically, activation function should be some differentiable, non-linear. Differentiable because we need to do backpropagation. If we want to do backward propagation, we always need to differentiate the loss function. So the activation function has to be differentiable. Non-linear because we need to use the non-linearity of activation function to make our neural network capable of dealing with the complex data, the non-linearly separable data. And this allows the model to learn some more complex functions. And there are three commonly used activation functions in hidden layers. ReLU, we already learned that, and sigmoid, we also learned that. So here is a new activation function we can use that is called hyperbolic tangent or tangent H. Let's first have a quick review about ReLU and sigmoid. So for ReLU, it's just the max between 0 and x. Note that it's the most common function used for hidden layers because it's very simple, very fast, very efficient. It's simple to implement and effectively overcome the limitations of some popular activation functions such as sigmoid and tangent H. Specifically, ReLU is less susceptible to the vanishing gradients problem. You may immediately ask why. Previously, when we are learning ReLU, we learned that actually ReLU has a limitation called dying ReLU problem. Dying ReLU means that if once the weighted sum is negative, then the ReLU deactivates such neuron. And in the meantime, the gradient becomes 0. So that means these parameters won't get updated. Then due to such dying ReLU problem, why the ReLU is still less susceptible to vanishing gradients? Later on, we will see that we will use the sigmoid and tangent H as some comparison to see that even though the ReLU has dying ReLU, but if we compare it with sigmoid and tangent H, we can say that it's relatively better, actually relatively better. So here is some like implementation tips. So if you want to use the ReLU function for the hidden layers, it's good to use some HE norm or HE uniform weight initialization. This initialization is trying to scale the input data to the range of 0 to 1 before training. Usually we try to normalize the input data. So if you want to use that, basically that's create an object initializer using this TensorFlow Keras initializer HE normal. Or you can also use this HE inform and then let the layer be this one, this dense layer. 3 is the number of neurons, the units, and let the kernel initializer be the initializer you have created. So this is some practical implementation tips if you want to use ReLU activation function. Then sigmoid, a quick review, we found that, okay, it's the 1 over 1 plus exponential of negative x. Actually, there is a limitation of sigmoid function we haven't mentioned before. When we are learning it in the artificial neuron, we kept it like as some remaining things. I say that, okay, when we are learning multi-layer perception, we will mention more limitations. And here is one limitation of sigmoid. So we find that the output of the sigmoid function is not symmetric around 0. Actually, it's symmetric around 0.5, right? When x equal to 0, fx is 0.5. So it's symmetric around 0.5. that's that value. So that means the output of all the neurons will be of the same sign, because we know sigmoid has a range 0 to 1. Actually, all of the output will be positive of the same sign. Actually, if all of the neurons have the same sign, their output, then the training of the neural network is more difficult and is not so stable. Because when these neurons try to learn parameters, try to know like which input or which features are more important, basically that will highly depend on the sign of the output, whether it's positive or negative or 0. But the sigmoid will just make all the output the same sign, all of them positive. Actually, it's not so good for training the neural network. So usually we require that it's better that this output can have different signs, and this output is better like possibly to be symmetric around 0. And this is one limitation, and very soon we will talk about how to solve this limitation by using hyperbolic tangent. Here is another note that if you want to use sigmoid for the hidden layers, you can use such normalization or initialization, the Glorot normal or Glorot uniform. Actually, this is again to scale input data to the range 0 to 1. So create an initializer using the Glorot normal and then create the layer using such initializer. So this is the sigmoid implementation. All right, we already see that the sigmoid has such limitation. It's not symmetric around 0. Then how to try to fix this limitation? And in the meantime, maintaining the good property of sigmoid, we have a very similar activation function, hyperbolic tangent, or the tangent H. So if we look at the mathematical formula, it's exponential of x minus exponential of negative x divided by exponential of x plus exponential of negative x. So this is called the hyperbolic tangent. If we try to plot this hyperbolic tangent, we find something like this. It's S-shape, very similar with sigmoid. Actually, if you observe the function, you find that it's very similar with the sigmoid. But note that now the difference that the hyperbolic tangent takes negative value. The value range of hyperbolic tangent is from -1 to +1. And when x equal to 0, this tangent h equal to 0. So that means actually this function is symmetric around 0. So some analysis of the hyperbolic tangent h is very similar to the sigmoid function, has the same S shape with, actually it's differentiable, right? It's smooth and differentiable. Good property can do the backward propagation. But the difference is that the output range of tangent h is from -1 to 1. And we also find that now the output of tangent h is 0-centered. When x is 0, is 0. So we can easily map the output values as some strongly negative, neutral, or strongly positive just by looking at the output value. So when used in the hidden layers, the mean of the hidden layers comes out to be 0 or very close to 0, roughly centered at 0. So it helps in centering the data and makes learning for the next layer much easier. So that's why actually if you want to use activation function in hidden layers, if you only choose between sigmoid and tangent h is usually much preferable than the sigmoid. It's centered at 0, and also it has like different signs for the different outputs. All right, so until now, any question regarding the hyperbolic tangent? Great, so we learned a new activation function. We still have one remaining question. Here we said that ReLU can effectively overcome the limitations of sigmoid and tangent h in the vanishing gradients problem. How come? So after we learn the tangent h, we can try to do some further analysis on sigmoid and tangent h. and try to get a sense why these two activation functions are more susceptible to the vanishing gradients. Actually, if we want to analyze that, we have to do the gradient. We have to differentiate the sigmoid and the tangent H. We find that their derivatives like this. This is the sigmoid gradients. Actually, when we are introducing sigmoid, we already said that the sigmoid gradient is sigmoid x times 1 minus sigmoid x. We use this to do some parameter update. And we find that it's something like this. So if you look into that, you find that only within a very small range, that is when x is from -3 to 3, this very narrow range, the gradient of sigmoid has significantly large value. And when x is less than -3, or when x is larger than 3, the gradient is close to 0, very close to 0. And this is exactly the vanishing gradients problem. Right? Vanishing gradients problem means that the gradient becomes very, very small, close to 0, and makes the update or the training very slow, or even just stops. But actually, it's not converged to some local minima. It's just because of the gradient is very, very small. And this exactly occurs for x smaller than -3 and x larger than 3 if we use sigmoid. If we further look at the tangent h, the tangent h derivative is the tangent hx square. So it takes some shape like this. So of course it has much larger value than sigmoid derivative, but still the range is very narrow. Again, the range is around from -3 to 3. This gradient has significantly large value. And for all the outside range, actually it meets the vanishing gradient problem. So after observing these two derivatives of the two functions, we find that the gradient values are only significant for the range -3 to 3, and the graph just gets much flatter in other regions. So for values greater than 3 or less than -3, the function just have very, very small gradients. And as the gradient value approaches to 0, the network just ceases to learn and suffers from the vanishing gradients. So that's why we see that the sigmoid and tangent H more susceptible to vanishing gradients. And that's why the ReLU actually is better, even better. So if you still remember the ReLU's derivative, maybe we can just draw it. It's in some previous page in the lecture notes. So the ReLU's gradient is something like this. This is 1. Okay. The ReLU derivative, of course, when x is negative, L is 0, that means in the negative part, actually, it suffers from the dying ReLU or the vanishing gradients. But still, as long as this x is positive, the gradient is 1. So that means actually it has a much wider range than the sigmoid and tangent H, because sigmoid and tangent H only has a significant value in such a narrow range, -3 to 3. But for ReLU, the range is quite wide. As long as x is positive, actually it has some significant derivative value. This is why the ReLU actually is better than sigmoid and tangent H if we consider the vanishing gradient problem. All right, so any question regarding these vanishing gradients and the different activation functions of their different behaviors? Great. Actually, this motivates us. That's why we should use the ReLU activation function in the multi-layer perceptron's hidden layers. And here is some more formulated rules how to choose a hidden layer activation function. So we already found that both sigmoid and tangent H function, they can make the model more susceptible to problems during training, where the so-called vanishing gradients problem. And the activation used in hidden layers is typically chosen based on the type of neural network architecture. So some modern neural network models with the common architecture such as MLP and CNN, we will cover CNN later, it uses the ReLU activation function or some extension of ReLU. So actually there are some like different activation functions. They are based on ReLU. But there are indeed some neural network architectures will use the sigmoid or tangent edge in hidden layers. That's the recurrent networks, RNN. So for RNN, it's a type of neural network that has at least one loop, so the edges goes back. So for RNNs, they still commonly use the tangent edge or the sigmoid activation functions, or even both. So here is a summary. So if we are using the MLP or CNN, then commonly we use the ReLU activation function in hidden layer. If we use RNN, then commonly we use tangent edge or the sigmoid activation function. So depending on the neural network architecture we're trying to learn. So this is for the hidden layers. And then we still need to decide the activation function for the output layer. So for output layer, actually the activation function, what the activation function output is directly outputs of the whole neural network. That is our prediction. And there are three commonly used activation functions for the output layer: linear activation function, sigmoid, and softmax. Sigmoid and softmax, we already learned that what is the linear. Actually, you don't need to learn what is linear. You already know what is linear, right? So this is the linear output. Fx equal with x. Just this straight line, the linear activation function. So the linear activation function is also called identity activation because it just multiplied by 1, or we even call it no activation. Because if you directly let what you receive as the output for this neuron, then basically that means no activation at all, right? Note that if we use the linear activation function, then it's not possible to use the backpropagation, as the derivative of this function is a constant. It's always 1, has no relation to the input x. And the target values used to train a model with a linear activation function in the upper layer, they are typically scaled before modeling using the normalization or standardization transforms. This is linear. And then what is the use of the linear activation function? Right? It seems no activation at all, and seems that's not proper to do backward propagation. Most of the cases, we won't use the linear activation function except the regression task. So the neural network actually can also be used to do the regression, not only for classification. If we are dealing with some regression task, then the linear activation function is proper. Because the regression means that we want to output a value in a continuous range, and then that means it's better to use this linear activation function to directly get what it accepts as a linear transformation. This is for linear, and sigmoids analyze it a lot. So sigmoids, even though we find that in hidden layers it's not so good because of the vanishing gradient, but in output layer, still sigmoid is quite good if we want to have a probability as the output, because we know that sigmoid have the values 0 to 1, which perfectly match probability. So if we are doing some binary classification, it's very good to use sigmoid. Then the softmax is the function that converts an array or a vector of numbers into an array of probabilities. And we also learn what is the mathematical formula. So this softmax is used for the multi-class classification because each of the output fxi is a relative probability, the probability of predicting the input as this class label. And if you add off them up, like the summation of all these fxi is equal to 1. So that's the probability. Of course, if you want to use this softmax, usually the class membership is required on more than 2 class labels, because in that case, it's meaningful to do the softmax. Otherwise, you can directly use sigmoid if you only have 2 classes. Sorry, the sigmoid here. All right, then let's try to do a summarization how to choose the output activation function. So we choose activation function for output layer based on the prediction problem you are solving, because all of the outputs from the output layer has the practical meaning, right? And the practical meaning of what is the final prediction. If a problem is a regression problem, then we directly use a linear activation function. If the problem is a classification problem, then we consider specifically which classification problem it belongs to. And there are 3 main types of classification problems. The first is binary classification. In this case, in the output layer, we only need 1 node with a sigmoid activation function, so that this output represents the probability of some positive class label. If it's a multi-class classification, then we need to use multiple nodes, 1 node per class, and all of them use the softmax activation function. We want the relative probability. If it's a multi-label classification, then we have multiple nodes, and 1 node per class, all of them use sigmoid activation function. So please know the difference between multi-class and multi-label. There are 2 different classification tasks. So if we're talking about multi-class classification, then we still have the assumption that each sample is assigned to 1 and only 1 label. It just the labels are from some multiple classes. If we're talking about multi-label classification, then each sample actually can be assigned to a set of target labels. We can take some news article classification as an example. If we're doing some multi-class classification, then our label set possibly can be this computer, science, society. That means each data is just 1 news article. Each news article will be assigned 1 and only 1 label from this set. So this article is like either computer or science or society. It cannot have like more than 1 class labels. This is a multi-class. But for multi-label label sets, it possibly can be like computer, science, society, operating system, cryptography, electronics, religion. In this case, for each data sample, that means each news article can have multiple class labels. For example, this news article can belong to operating system. If it belongs to operating system, then it also belongs to computer, right? Actually, these class labels, they overlap with each other. And if a news article belongs to religion, then it also belongs to society. It can have like these 2 class labels, society and religion. So this is a multi-label classification. 1 data sample can have like more than 1 class labels, can have multiple labels. And actually that's why for multi-label classification, we use sigmoid activation function. For multi-class, if we use softmax, then the prediction is that we directly assign the class with the highest probability to be the prediction. But for multi-label, we use sigmoid. Then we decide a threshold. Usually the threshold is 0.5. So that means as long as the node has larger than 0.5 probability, we will classify the data into that class label so that it has like multiple class labels. So this will be the difference. And which activation function you use and how to arrange the nodes in your output layer depends on which prediction task you are dealing with. All right, hope this will be clear to you. So any questions so far regarding how to choose output activation function? Great. If no question, our very last question would be like when to use the multi-layer perceptron. So they are suitable for the classification prediction problems where the inputs are assigned a class or a label. This is what we have used as examples in the lectures. In our lectures, like the XOR logic relation and also the handwritten digit recognition, we are all use them as the classification. But note that MLPs are also suitable for regression prediction problems. In this case, a real valued quantity is predicted given the set of inputs. And the data is often provided in some tabular format such that we would say in some CSV file or a spreadsheet. Actually, we know we can use pandas to deal with data. And we use the regression problems, the output layers activation function usually is a linear activation function, which we have just summarized here. So MLP can be used for both classification and regression. But of course, the activation function in output layer will be different. All right, so at the end, we appended a practice problem for you. So you can try to solve this. Now we only have like 2 data points in our training set. So you can just try to do some forward propagation and backward propagation to see whether you already get a good understanding of the updating rules of MLP. So until now, any question so far about the whole MLP lecture? Great. If no question, then let's take a 5 minutes break. After the 5 minutes break, we will have some simple quiz on MLP using Mentimeter. And also, we will go into the new topic on the image processing. So let's take a break.
Softmax 的时候已经有 assumption 了，就是他们是 relative probability， 就已经默认了说，当一个 input 它的 probability， 比如它是属于第一个 class 的时候，这个 probability 和它属于第二个 probability 的时候是彼此互 overlap， 它们加起来都是 exclusive， 对，所以他们才能相加等于。一般就是用 threshold， 就是如果它大于0.5。那我们这个就相当于用了这个但是 step 是做 back propagation。就是说那就是说在 forward 在这种预测的时候，类似的，但是用这个思维方式是为了方便。对，就是为了做 back propagation。那我们这个地方，我就是怎么理解它是猫的更 C。就或者说换言之，我把所有流动加起来取出概率，这个做这个概率，那我理解。但是我们说一加1的 x 分之，那这个东西它是一个一加这个东西，就是它怎么说呢？就我不是理解这 C， 我也就是你可以就是把它重写一下。对，所有的那个床对，是剩下的，对，就是以上，应该就是这等于。其实就是这样的，对，然后就是就是这种，对，就是用它其实等于是。我有那个上下。
这个意象，这是什么意思？
哦，就是这一项，因为如果是 sigmoid 的话，其实它这个整个就 sigmoid 的时候就因为 sigmoid 是这样，对，就相当于如果这一项是一，它就直接是sigmoid，但是这一项并不是一，而是这一项是用一减去了它本身的那个东西，相当于是一个剩下。对，就是剩下所有东西的一个 relative。
所以说这是个近似。
对，它是个近似，只能是近似，而不是真的 sigmoid。
哦。
如果把这个换成 D 的 flex 方法，
上面那个和下面是一。
对，如果这个和是对近似乘一的话，其实它就是直接是个 sigmoid。
哦，这上面。
对，上面。
但是上面不一定是一。
对，上面都不是一，其实上面一般都不是，它所以就是一个近似。
然后两边拍 forward 的时候就用那个 backward 就不能换。其实我觉得其实你想用的就是这个，但纯粹
那就没法修导。
用语言去方式说字面，
对，
然后
一个诺里找不到，我现在开始在 X 更小。
太惨了。
说实话，一取啥都就是那个，就是纯粹的好
对
看。
然后，这个也是三本，他认为是 mutually exclusive。
All right. After this short break, before we going into our next lecture, the image processing, let's do a simple quiz on the MLP to assess that whether you already understand some of the key concepts in the MLP. So you can scan the QR code to join this Mentimeter quiz. Yeah. And also, like, you can look at this figure. So this is a neural network. And the neural network commits mistakes. Usually we know that in early iterations, in early training, the neural networks always make lots of mistakes, right? That's the error function. And the neural network learns from its mistakes. Each time it makes some errors, it uses that error to update all the parameters so that it can be more accurate. So the neural network works hard to attain the perfection so that at the end, the accuracy will be very high. So wish you all of you be like a neural network to learn through your efforts and learn from your previous mistakes to attain the perfection. Right, so be a neural network. All right, so has everyone joined yet by scanning this QR code? Great. If yes, then let's start. Okay. Yeah, majority can get it correct. This is true. If the learning rate is very, very small, then that means at each step, the change of parameters is very small. In this case, the training is quite slow. the gradient descent may take a very long time to converge because each time you just like change the parameters by a very, very small length. And so it's quite computationally expensive if the learning rate is too small. Yeah, it's very good majority can get it correct, but it doesn't matter if you get it wrong. You can learn from this mistake, and next time you will get to that. So let's check the leaderboard. Okay, even though midterm below me, but for this quiz, yeah, you are doing quite good. Okay. Let's see the question 2. Okay, this is false. Increasing the number of hidden layers will cause the overfitting problem. That means if your data is not so complex, but you still use many hidden layers, then actually your model like just easily get overfitting on the training data. It does not increase the model performance. Actually, it will impact the performance on some new data, generalization ability to the testing data. So this is false. Okay, now our number 1 is like Maverick. Then let's check the question 3. Okay, this is quite tricky. Actually, if you want to deal with binary classification, softmax is also okay. You can use, even though usually if it's only binary classification, like we typically just use one node in the upper layer with sigmoid, right? But actually you can put 2 nodes in the upper layer and use the softmax. It's also okay. So both softmax and sigmoid can be used as activation function in the upper layer if the binary classification. So this is true. Okay, our Maverick is still number 1. Yeah, don't know where the midterm below me goes. Okay. The next one. Okay, this is false. Validation accuracy is possible to be higher or to be lower than training accuracy. It's all possible. Actually, it depends on the data. Usually, we say that like because the training is trained on training data, so usually the training accuracy possibly like is higher than validation accuracy, but we also need to consider that usually the training data is very large and validation data is very small. When you're testing in a quite small data set, then the accuracy may even be higher because it's relatively easier. So that means it's not like so easy to get some mistakes. So actually both can happen. There is no must rule that the validation accuracy must be higher or lower. We don't have such rule. Basically just everything is possible during the training. So this is false. Okay, Maverick is still number 1. Then last question. Okay, this is true. Actually, this already defines what is the goal of training on MLP. The goal of training on MLP, we know that actually it tries to optimize the loss function or to minimize the loss function by adjusting the network's parameters. So each step, it tries to update the parameters so that the loss function can be further minimized. This is achieved through the backpropagation. Yes, through backward propagation, actually all the parameters get updated so that the loss function can get decreased. This is true. Basically, this is the goal of training on MLP. All right, let's check the final leaderboard. Okay, midterm below me occurs again. Okay, yeah, congratulations to today's number 1 Maverick. Who is Maverick? Oh, okay, congratulations. Yeah, very good. So, any question regarding these quiz questions? All right, if no question, then we can move on to start our next topic, the image processing. So in this lecture topic, we will learn some digital image processing fundamentals. You may have some confusion, right? This is an AI course. This is not a CV course or image processing course. Why should we learn some digital image processing fundamentals? Actually, this is our ultimate goal, is to learn the convolutional neural network, the CNN, which is another type of artificial neural network applied to analyze the visual imagery. Actually, right after we learn image processing, we will start to learn the CNN. However, the research has demonstrated that pre-processing images before feeding them to CNN would significantly improve the classification and recognition accuracy. So that's why to learn how to pre-process images and use this powerful tool to tackle the computer vision tasks, you will first learn the digital image processing fundamentals. Like only after you already learn how to do image processing, then you can try to fit all these processed images into some CNN so that the performance will get good. But you can have a advanced view on what is a CNN. So it's very like the MLP, right? Roughly looking, it's very like, but still there are differences. First of all, the input is some 2D imaging. And here actually is RGB channel. So actually this is 3D. This input is 3D. And actually we don't do flatten. So that means CNN can directly accept some multi-dimensional images as some input. No need to flatten. And after this, accepting this input, it will be some kernel layer. Later on, we will also learn what is kernel. Actually, just in image processing, we will learn some kernel by learning the image convolution. after some kernel layer, it has some like output channel, and connecting with like some multiple kernels at the end, we still have the output layer, and the learning mechanism will be exactly the same with MLP. So that means when we are training the CNN, we do one forward propagation. After forward propagation, we have the loss function at output layer, right? This is the neural network's loss. We need to do the derivative of the loss function to do some back propagation to update all the parameters in this direction. So the learning mechanism is still the same with MLP, but the layers used in CNN will be different. So I think in next week, we can start to learn the CNN, but before that, we learn some imagery pre-processing knowledge. So imagery pre-processing refers to processing an image so that the resulting image is more suitable than the original for some specific application. Here, a pre-processing method that works well for one application may not be best for another application. So it depends on specific application you want to deal with. And here are some very commonly used pre-processing tasks. Actually, we can try to compare this to this would be the description, and this would be the effects of this pre-processing. Like the shading correction is that we try to adjust the image inconsistency generally seen on the edges. And this inconsistency possibly due to some illumination and the background inhomogeneity. As you can see, the shading correction, they are like quite inconsistency, especially in some edges. And after shading correction, we can get some resulting image like this. And the second type is called deep blurring. I think the effects is quite straightforward. So the deep blurring means that you remove the blurring artifacts from the images to restore the original and sharp content. So after deep blurring, you will get a quite clear, quite sharp resulting image. And we also have like denoising. So for this denoising, of course, then you remove or reduce the noise from an image and to recover original image. So after this denoising, like in the original image, it has quite a lot of noises, but after that, you will get a less noisy content. And for the contrast enhancement, so contrast enhancement is to touch up the contrast of the image, or you can consider this contrast is some difference in color and light between part of it, so that you can improve the image perception by human eye. As you can see, the original image is not so clear to distinguish for our human eyes. Even though it might be good for some like machines, but not good for human eyes. And then after this contrast enhancement, this is relatively clearer to see, right? So that our human eyes can capture the information from the resulting image. So these are some like commonly used image pre-processing methods. Later on, actually, we will learn the technical details of these pre-processing methods. So the DIP, digital image processing, this is a method to manipulate a digital image to either enhance the quality or extract relevant information. Usually we consider that enhance the quality is more like for human eyes, because like humans have the need to look at some images, and extract relevant information usually is considered as it will be fed into some neural network or into some machine learning model. So we need to like make the images like easier to extract its relevant information by the neural network. And these methods provide the foundation to pre-process images that are more suitable for some specific applications. So next, let's see some digital image fundamentals so that you can have some background to know how to manipulate the images. First, what is a digital image? So strictly defining that the digital image is a two-dimensional grid of intensity values represented by this I, X, Y. So here I represent intensity, X and Y are coordinates. And the value of I at the coordinates X, Y is called intensity. In the coordinate system, usually we call pixel. So in digital image, we use this pixel to represent each coordinate. So the pixel is short for picture element. A pixel is just a single point, or you can consider a single dot in the imagery defined by a coordinate x, y, single point. And then the dimensions of an imagery specified by the width and height of the imagery. So imagery width is the number of columns in the imagery. Imagery height is the number of rows in the imagery. Like here, this is an imagery of dimensions 32 by 21. So that means the imagery width, this direction, has 32 pixels, or we can consider that it has 32 columns. And imagery height, this direction, has 21 pixels, or you can consider it has 21 rows. This is the digital imagery, the dimension of the digital imagery. And we can further look into the coordinate system of the digital imagery. So a specific pixel in imagery is defined by its coordinates x, y. Note that it's different from the Euclidean space coordinate system a little bit, because now in image coordinate system, x is increasing from left to right, but y is increasing from top to bottom. So then now the origin 0, 0 actually is at top left corner. This is quite different with the Euclidean space coordinate system. Origin 0, 0 is here. So this is the coordinate system. And x increase from left to right. This is consistent. But y increase from top to bottom. So that like this pixel has a coordinate 0, 1, and this pixel has the coordinate 0 height minus 1. So this is quite different. In the digital imagery, we all follow such coordinate system. We always put the origin at this top left corner. And here in an image coordinate system, the legal range of x coordinates then is between 0 to y minus 1, because it starts with the index 0, so it ends at y minus 1. And the legal range of y coordinate is between 0 to height minus 1. This is the image coordinate system. Note the difference between Euclidean and this image system. Then there are like different types of digital images. The grayscale imagery is a range of gray shades from black to white. So they are commonly used in the image processing because the data are smaller, because we don't need to store the color information. Now in the grayscale images, basically there is no concept like color. You don't need to consider any color. We remove all color information. So that's why the data are smaller. And when the data are smaller, it allows us to process the images in a quite short time. A grayscale digital image is an image in which the value of each pixel carries only intensity information. So at each pixel, it only has one value, that's the intensity value, and it contains 8-bit pixel data. Here 8-bit means that it has 2 power of 8, which is 256 different gray levels. And actually that's why for the intensity value, it must be an integer from 0 to 255, because they are stored in this 8-bit data. So from 0 to 255. So here 0 is black. So there are some grayscale, their value and their like different grayscale. So when gray level is 0, it's just black. And when the grayscale is like 127, here it would be the medium gray like this. And when it's the maximum value, when the intensity or the grayscale is 255, then it becomes white. So if you select different gray level, then basically you are selecting the different grayscale, like from black to white. So this is the grayscale imaging. And if you want to have the color information, then you don't have to use these grayscale images. If you want to store that color image, then you use 3 channels, that's RGB. So these color images, they have intensity from the darkest and the lightest of 3 different colors, red, green, and blue. So any color in this digital image can be regarded as a mixture of these three colors intensities. So the RGB images, actually it contains 3 times 8-bit intensity, right? Each channel has 8-bit intensity. Each channel can take value from 0 to 255, and we have 3 channels. So this RGB also referred to as some 24-bit color images. And there are some common colors represented in RGB. So if RGB takes the value 0, 0, 0, then again it's black. If RGB, like all of them take 255, then it's still white. So each of the possible color in a digital image is just a mixture of these 3 channels. If you want some pure red, then let the red be 255. Green and blue be 0, and if you want some pure green, of course you can let the green channel be 255, and the same for some pure blue. If you want some mixtures of the colors, like if you want yellow, then let the red and green be 255, blue be 0, then you can get this yellow color. And for gray, you can let all of them be 128, and dark gray would all of them be 50. So you can just create different colors using the different mixtures of these 3 channels. There are special type of these 24-bit grayscale 24-bit images is called 24-bit grayscale images. So they are a subset of RGB images when the RGB intensity are all equal. If you find that all of the 3 values are equal, then they are called 24-bit grayscale images. Like here in this table, black, white, gray, dark gray, actually they are 24-bit grayscale images. Their RGB are equal with each other. Note that for these 24-bit grayscale images, actually they can be represented by grayscale images. Actually, they can be represented if you directly use this grayscale. So this will be the color images. So any questions so far regarding grayscale imagery and color imagery? All right, there's just some fundamental introductions about the different types of images. Next would be how to manipulate the images in Python. So if you want to access images, usually we just use the Google Drive. So you first need to mount your Google Drive to Colab. I believe this is already like very familiar to you if you finish like these labs. Like first from the google.colab import drive, and then we also need to import some OS and system modules, and then we mount the Google Drive and we go into this folder. Suppose that there is a folder images already created in our Google Drive, and then we add this path for interpreter to search. All right, after we mount in our Google Drive folder, we can try to access and read some images. To read an image, usually we use this library, matplot library, and we import it, give it a nickname, this MP image. So we use this method in read to read the images. This would be the syntax. This f name is the image file you want to read. It's a file name or some file-like object operated in this read binary mode. And this format by default is known. So this format means the image file format assumed for reading the data. If the format is not given, then it will be deduced from the file name. For example, if you give like an image .jpg, then it will deduce that the format is JPG. Or if you give a file name like image.jpeg, then it deduces, okay, the format is JPEG. If nothing can be deduced, then by default is PNG. So if you didn't give the format and this function cannot read the file name, the extension of the file name to import the format, then it will try to read this image as some PNG. The return value of such imRead method would be a NumPy array. Yes, in this Matplotlib library, all the digital images, actually, they will be read as some NumPy array. So the NumPy array have possible different shapes depending on which type of images you are giving. Like if a grayscale images, then for each pixel, it only has one intensity value. So it will read a NumPy array with the shape M, N. So M and N is the shape of the image, the width and height. So it will directly read such 2D array. If it's an RGB image, then the array will have 3 dimensions. So the shape would be MN3. So that means MN, again, the image's shape, the image size, width and height, and then this 3 is the RGB channel. Like for each color, you have a channel, so it's MN3. Another type of image is RGBA image. Even though we don't use it quite often in these lectures, but still it's like when you are like reading or manipulating your own images, possibly you will deal with such kind of image. It's RGBA. So in this case, it has 4 channels: red, green, blue, and alpha. The last one we call it alpha. We can regard this RGBA as some 3-channel RGB color model supplemented with a 4th channel called alpha. So here this alpha indicates how opaque each pixel is. So that means the last channel A alpha representing the transparency information. So as you know, actually different digital images, sometimes they also have such transparency information, different level of transparency. So in this case, RGBA image has the shape MN4 because it has 4 channels. And now that the return value in such NumPy array, usually we see that the digital images are 8-bit images. So that means there are some integer values from 0 to 255. But this only has one exception for PNG images. If it's PNG images, then all the values, there are some float values from the range 0 to 1. That means PNG images, they actually normalize the intensity values. Normalize from the range 0 to 255 into the range 0 to 1, and all of the values are just some float values, only for PNG. All other formats, actually, they will return some integer arrays with the value 0 to 255. And actually, that also explains why usually the PNG images is smaller than other image formats, right? If you check your images, your photos, possibly in your own computer, in your own smartphone, you'll find that usually the PNG images consume less memory. This is because the PNG images actually they contain float values from 0 to 1, but all other images actually they are 8-bit. The integer values from 0 to 255. All right, so this would be the syntax of this inRead function. We can try to, haven't gone into the example here. All right, then maybe for this class we just end here. So for next class, we will continue to introduce more functions like how to show image and how to save image, and then we will see a specific example to let you know how to use all of these methods. So see you in next class. That would be on this Thursday. And tonight we will have the paper checking session for the midterm exam. So if you want to check your paper, you can feel free to come to the paper checking session tonight. I think that would be the neighboring classroom, the room 4621, for tonight's paper checking. All right, so see you in next class.